Hello, and welcome to your third lesson in Unit 6, where we're going to be talking about precipitation. So, I'm not talking about rain or any other type of water falling from the sky, right? Precipitation, we're talking about a solid forming from aqueous solution. So, up until this point, we have been talking about a solid dissolving into ions. Now, we're just going to flip it and look at the reverse, those ions precipitating back out into the solid form. So in order to consider precipitation of ions, so them coming out of solution to form a solid, we are actually going to bring back the concept of Q and K. So if you remember way back from Unit 3, we can calculate Q at any point in time. Typically, it is initial conditions. And then we can use the value of Q and compare it to K to then determine which way an equation is going to shift or an equilibrium is going to shift. So if Q is less than K, we got to go to the right towards the products. If Q is greater than K, we got to go to the left towards the reactants. And if Q does equal K, then we are already at equilibrium. This is the same concept for Q and K when we're talking about solubility. So, as we said, precipitation is the formation of a solid from solution. So we can determine if ions are going to precipitate out and form a solid by calculating Q, and in this case we're going to call it QSP, using whatever initial conditions or initial concentrations that we are given. So just like in the previous slide, when Q equals K, we're at equilibrium. Well, when we're talking about ions in a solid, equilibrium, we call that a saturated solution. So if Q is equal to K, then our solution is saturated. We're at equilibrium. If Q is greater than K, so Q is greater than K, we're going to shift left. Precipitation is going to occur until Q equals K. That's, in other words, a supersaturated solution. So if we have a solid and Q is greater than K, we have to shift left, meaning we're going to be forming solid. The term for that is precipitation. If Q is less than K, we are an unsaturated solution and no precipitation will form, or no precipitate will form, because we're shifting right. So instead of any precipitation happening, we're actually dissolving more solid. So it's the exact same concept of Q and K. It's just now we're applying it to dissolution and precipitation, which are reverse reactions. So in order to determine if a precipitation will occur, we are going to look at what we are given. So we are given two solutions here. So we are told the concentration of magnesium ion in seawater is 0.0537. Will magnesium hydroxide precipitate when enough calcium hydroxide is added to give a hydroxide concentration of 0.001 molar? Now, in this particular question, we are not dealing with a volume change because instead of creating a solution, we are just told that the concentration of magnesium is 0.0537 and the concentration of hydroxide is 0.001. So I write my equilibrium here, and then I write my Q expression. These zeros right here are just indicating initial. So initially, I have 0.0537 magnesium and 0.001 hydroxide. We write Q just like we write K, raised to their coefficients. We have no denominator because it's a solid and solids don't appear. So when we multiply this out, we get that Q equals 5.4 times 10 to the negative 8. So now we're going to compare Q to K. Well, in this case, Q is greater than K. So whenever Q is greater than K, we shift left Well, in this case, shifting left is making a solid. So ions will precipitate. So if you were asked this question, you would say there will be precipitation because Q is greater than K, and you can show that with the math. So let's look at this example. Does silver chloride precipitate when 100 milliliters of 2.0 times 10 to the negative 4 molar solution of silver nitrate is added to 100 milliliters of 2.0 times 10 to the negative 4 solution of sodium chloride? So immediately we see that this question is a little bit different than the previous question because we are adding two solutions together. So this is similar to when we were creating buffers. When we add two solutions together, we're changing volume. When volume changes, concentration changes, okay? So when we are combining two solutions of aqueous ionic compounds, the first thing that you need to consider is, what is the precipitate? So for this example, we are combining silver nitrate and sodium chloride. So our two options are silver chloride is going to be one product and sodium nitrate. Well, we know that nitrates are never insoluble. Group 1 metals are never insoluble, so my precipitate is definitely silver chloride. So then I'm going to write out my silver chloride equation, and you would have to be given that the KSP is 1.8 times 10 to the negative 10, or maybe you calculated it in a prior problem. So the first thing I have to do is I have to take care of the volume change. So remember, so the second thing, volume change. Remember, what we're going to do is we're going to multiply the molarity times the volume, and then we're going to divide it by the new volume to get the new concentration. Now, I only did this one time for this problem because I had equal concentrations and volumes. So both of their new concentrations are 1 times 10 to the negative 4. So then I'm going to write my Q expression, concentration raised to the coefficients, which in this case were both 1. So then I plug in my new concentrations and I get 1.0 times 10 to the negative 8. Well, I'm going to compare that to the K value, and Q is again greater than K, and so the ions will precipitate out. Okay, so let's do an example. So we are combining silver iodide with silver nitrate. So first things first, what is the precipitate? So our options are silver iodide and calcium or potassium nitrate. Now, this problem tells me straight up that it's silver iodide, but if you were not told, then you need to make sure you recognize that it is the silver iodide that's going to precipitate, not potassium nitrate, because nitrates and group 1 never insoluble. Okay, so second thing, we're going to deal with the volume change. So at this point, it is the silver from silver nitrate that I'm concerned with, so I'm just going to do this as the silver concentration because the nitrate is just going to be a spectator. If we need to think about this, so we have one solution of silver nitrate, which of course is actually the ions. We have another solution of potassium iodide, which also is in the ions. So then when we combine this together, we have all the ions floating around, and it's when these two come in contact that they're going to form the solid, and these are still just going to be hanging out in solution. So the silver ion concentration, it was 0.1 molar. We had 10 milliliters of it. So that's 0.01 liters. So that gives me 0.001 moles. Then I divide it by the new volume, which is 10 plus 90, which is 100 milliliters, which is 0.1 liters. And my new concentration of silver is 0.01 molar. And then for the iodine ions, again, it's for potassium iodide, but it's the iodine ions that are actually going to contribute to my precipitate. So originally it was 1 times 10 to the negative 10 and 90 milliliters, so 0.09 liters. So that gives me 9 times 10 to the negative 12 moles divided by my new volume, which is 0.1 liters, gives me 9 times 10 to the negative 11 molar. I have a very, very low concentration of iodine, and I have a generally normal concentration of silver. Whoops. So now I'm going to calculate Q. So Q is equal to the concentration of silver times concentration of iodine. Both of them raised to the 1 because their coefficients are 1. So I'm going to plug in 0.01 times 9 times 10 to the negative 11, which is going to give me 9 times 10 to the negative 13. So that is Q. So now let's compare So Q, 9 times 10 to the negative 13, compare it to K, it is greater than K. So when Q is greater than K, we have to precipitate. So even though this seemed like such a low concentration of iodine, because the K value is so small, and this is such an insoluble solid, even that tiny amount is going to create a precipitate. All right, so we're going to do another example. So this time we're just told the ions being added. We aren't given the full salts, but we are adding 2 solutions together. So again, we have to deal with our volume change to get our new concentrations. So for potassium, we had 0.05 molar, and we had 20 milliliters of it. So that gives me 0.001 moles. But then my new volume is 0.1 liter. So I get 0.01 molar of potassium. And then I have the chlorate ion. I have 0.5 molar. 0.08 liters gives me 0.04 moles divided by my new volume gives me 0.4 molar chlorate. Now, if you look here, our K value is much greater. So there is a definite chance that this won't precipitate because this is a pretty soluble salt, which we expected because potassiums are typically soluble, all group 1. So everything is relative. So now I'm going to calculate Q. Both these coefficients are 1. Again, if you needed to write it out. Both the coefficients are 1. So I'm going to plug in my values. And I get 0.004, which if it makes it easier to compare in scientific notation, we could write this 4.0 times 10 to the negative 3. So for this one, Q is actually less than K, so no precipitate is going to form. So everything would just remain hanging out in solution. Okay, so now that we've learned how to determine if a precipitate will form or not, now we can actually take it a step further and decide what are the new concentrations going to be after the precipitation happens. So in this example, I'm told a solution is formed by mixing 100 milliliters of 0.05 molar lead nitrate and 200 milliliters of 0.1 molar sodium iodide. What are the equilibrium concentrations? So the first thing I'm going to do is what I was doing in the past 2 problems. Will a precipitate form? So that's step 1. So first of all, I need to recognize that the precipitate that could form is lead iodide. So this has to be the KSP value for lead iodide. And I have to do my volume change. So I told you the Q on this slide, but I'm going to go through the work to solve for that Q. So originally for the lead, I had 0.05 times 0.1 liter equals 0.005 moles. My new volume is 0.3 liters, so that gives me 0.0167 molar lead. And then for the iodine ions, I had 0.1 molar and 0.2 liters of it, so that gives me 0.02 moles divided by the new volume gives me 0.067. Oops. Now this time I have a coefficient, so I got to raise that iodine concentration. I got to square it. So I plug in my values, 0.0167 times 0.067 squared gives me 7.5 times 10 to the negative 5. So now you see where I got this value. And when compared to K, it is greater, so a precipitate is going to form. So that was step 1, determining if, in fact, a precipitate is going to form. Now, step 2, we have to determine how much precipitate is going to form. Now, since the K value is so small, we can assume that the maximum amount of precipitate is going to form. So you're going to use up every bit of one of the reactants. So what I did is I rewrote the equation in the reverse direction, so the ions turning to solid. I had the molarity and the volumes to get moles. So then we see that we have less lead than we have iodine. So that's the one that's going to run out, which is going to leave us with no lead left over, but it leaves us with 0.01 moles of iodine. And then I divide that by my new volume, which was, remember, we had 200 milliliters plus 100 milliliters. So that gave me 300 milliliters. And so this is my concentration of iodine that's left over. So now we can kind of use that leftover iodine as like a common ion, because basically what's going to happen is we said, okay, that much precipitate is going to form, but then I'm left with 3.3 times 10 to the negative 2 iodines. I had no lead left. So those are my initial concentration for the re-establishing of the equilibrium. So now I'm doing just a normal ice chart for dissolution. So plus x plus 2x, x, and 3.3 times 10 to the negative 2 plus 2x. Again, remember, these came from step 2. So then, because my K value is small, I get to ignore the x, the change in x right here, so I can ignore that. So then when I solve for x, I get 3.3 times 10 to the negative 2. So then, 1.3 times 10 to the negative 5. So then the concentration of lead is 1.3 times 10 to the negative 5, and the concentration of iodine is 3.3 times 10 to the negative 2. So that's going to be the new concentrations after the precipitation occurs and we reestablish equilibrium. So let's do an example. So we are told we have a 50 milliliter sample of lead nitrate added to 50 milliliters of potassium chloride. Calculate the equilibrium concentrations of lead and chlorine at equilibrium. So first thing we're going to do is determine, will this even precipitate? So we have to calculate Q. So I'm going to take care of my volume change. Lead iodide is going to be my precipitate if it forms. So my lead concentration from the lead nitrate, 0.1 molar, 0.05 liters. is sorry, trying to find the word. Oh, there it is. Okay. 0.005 moles over 0.1 liters is my new volume. That gives me 0.05 molar for the lead. And then for the iodine, we had 1 molar, 0.05 liters, gives me 0.05 moles, divided by 0.1 liter, gives me 0.5 molar. So now Q equals the concentration of lead times the concentration of iodine squared. I'm going to plug these values in. 0.05 times 0.5 squared gives me 0.0125. So that's my Q value. Now when I compare Q to K, Q is greater than K, so it will precipitate. So that was step 1. So now step 2, I have to do the precipitation. So I'm going to rewrite this in the reverse direction because we want to see how much precipitate forms to see how much excess ion we have left over. So we have, I'm just going to take the moles to plug in because we already converted to moles up here. So I'm just going to plug those in. So we have 0.005 moles. You cannot read that. And we had 0.05 iodine. Obviously, we have a limiting amount of lead, minus 0.005 minus 2 times 0.005 leaves me with 0 and 0.04 molar. Now, those are my initial concentrations for when I reestablish equilibrium. So I ran out of, so I'm taking these here and I'm plugging them in here. So I had no lead left over, but I do have 0.04 molar iodine left over. Oh, wait. Is it? Oh, whoops. Hold on. I'm silly. This was moles. Now I got to divide by my new volume, which is 0.1, which gives me 0.4 molar. Sorry about that. So I had no lead, and I had 0.4 molar iodine left. So plus X plus 2X, 0.4 plus 2X. Because K is so small, I can ignore that change in X. So I have X times 0.4 squared. So X equals 1.0 times 10 to the negative 4. And so that is my concentration of lead. And then 0.4 is my concentration of iodine. So we'll do one more practice. This time we're combining magnesium nitrate with sodium fluoride. So my precipitate is magnesium fluoride. So first step, does precipitation happen? So my magnesium concentration, 0.01 molar times 0.15 liter is 0.0015 moles divided by my new volume, which is 0.4 liters, gives me 0.0. Hold on. Yeah, okay. 0.0375 molar. And then for fluorine, I have 0.1 molar times 0.25 liters, which gives me 0.025 moles divided by 0.4 liters, 0.625 molar. So I just calculated my new concentrations. Then I'm going to plug them in for Q. Oops. Left out a number there, 0.0625 squared. And I get that Q equals 1.46 times 10 to the negative 5. So when I compare that to the K value, Q is greater than K, so this is going to precipitate. So now I'm going to do the precipitation. I'm going to take the moles of each. So I see I have a limiting amount of magnesium. So that's the one I'm going to run out of. So I'm going to have no magnesium left over, but I'm going to have .022 moles. I'm going to divide that by my new volume, which is 0.4, which gives me 0.055 molar. And I realize that I have a habit of doing it moles to volume, but you could just plug molarity straight in here because we already took care of the volume change. So you don't even have to worry about doing moles. You could have just plugged in 0.00375 and 0.0625 in. So you could do it either way. You're going to get the same answer. So then we've got to re-establish equilibrium. So again, this is almost like there being a common ion. We didn't have any magnesium left. We had 0.055 molar fluorine. We're going to set that equal to K so that we can solve for X. We get to ignore this. And so I get that X equals 2.1 times 10 to the negative 6. Make sure that's right. Yep, 2.1 times 10 to the negative 6. So that is my concentration of magnesium at equilibrium. And then my concentration of fluorine at equilibrium is 0.055 plus 2x, which would just round to 0.055. All right. Thanks for listening. There'll be practice problems for you to do in the problem set and for the notes assignment.